Hello, good day everyone. So today I'm going to present to you my assigned task, which is solving problems including several equilibria. By the way, I'm Alice Leon Rivera from BS Ed Science 3A. So in this video, we're going to learn what a chemical equilibrium is, learn how to calculate an equilibrium constant, and learn the Rice method for determining concentrations of chemicals at equilibrium, and of course solving problems involving several equilibria. So what is an equilibrium? Equilibrium occurs when opposing forces or actions are balanced. It's kind of like a tug of war. When the two sides pull equally, nobody goes anywhere, even though they're pulling with a lot of force. But tug of war is a static equilibrium. The chemical equilibrium is a dynamic equilibrium, that is, a chemical equilibrium involves constant motion, kind of like a water fountain. The water is constantly in motion, but it stays in the same place, more or less. A chemical equilibrium occurs when the forward and reverse reaction rates are equal, that is, reactants constantly react to form product, and products constantly react to form reactant, and the two things happen with the same speed so that the amount of each chemical stays the same. So consider the following reaction. Nitrogen reacts with hydrogen to form ammonia. So this reaction is known as the Haber-Bosch process. And like nearly all reactions, it can also go in reverse. That is, ammonia will also decompose to form or reform nitrogen and hydrogen. So what does that look like? Suppose that we have a 1 liter container and we fill it with 2.8 moles of nitrogen, 4.4 moles of hydrogen, and an appropriate catalyst. So we heat the mixture to 450 degrees Celsius. And we observe that the concentration of nitrogen and hydrogen decrease as they turn into ammonia. So after a while, however, the concentrations of nitrogen, hydrogen, and ammonia no longer change. So there are 2 moles of nitrogen and 2 moles of hydrogen and 1.6 moles of ammonia. So those amounts do not change no matter how long you wait for. So you might think that the reaction has stopped, but it hasn't. Rather, the reaction has reached equilibrium. That is, the chemicals are still reacting and never stop reacting. So the amounts do not change because new ammonia is formed at the same rate. Old ammonia decomposes. So keep in mind that equilibrium is not a special type of reaction. In fact, nearly all chemical reactions are equilibrium reactions. They just might not appear the way because they strongly favor the products. They are very slow, or product is removed from the reaction mixture. Now we can use our knowledge of kinetics to describe an equilibrium in a very useful way for the Haber process. So the rate of the forward reaction is a rate constant times the molarity of nitrogen times the molarity of hydrogen raised to the third power. Remember that the rate law is typically just a constant times the reactants raised to the power of their coefficients. Likewise, the rate of the reverse reaction is another rate constant times the molarity of ammonia squared. Remember that at equilibrium, the forward and reverse reaction occur at the same rate. So these two expressions are equal. So I'm going to erase the words so that we can focus on the two. So equal rate laws now. The two equal rate laws now that I want to do is to put all the variables on one side and the constants on the other. So let's see what happened. If I divided both sides of the equation by K2 N2 H2 to the third on the left side, N2 over N2 cancels out, as does H2 over H2 on the right side. K2 over K2 cancels out. That leaves me with K1 over K2 equals NH3. to the second over H and 2H2 to the third. Because Kl and K2 are both constants, the ratio is also constant, and that is a special constant that we call the equilibrium constant. So we call this constant KEQ for equilibrium constant, or Kc for the concentration equilibrium constant, or simply just K. Capital K, that is lowercase k is for a rate constant, and uppercase k is for equilibrium constants. The equilibrium constant is a physical constant for a specific reaction at a specific temperature, and it tells you about the reaction in general. The equilibrium expression of any reaction is that the equilibrium constant is equal to the molarity of the products raised to the power of their coefficients divided by the molarity of the reactants raised to the power of their coefficients. So let's calculate the equilibrium constant of the Haber process at 450 degrees Celsius. To do that, we're going to use the equilibrium expression of the Haber process and plug in the molarity x raised to the power of 1 at equilibrium Kc equals 1.6 squared divided by 2 times 2 cube, which is equal to 0.16. So interestingly enough, equilibrium constants are unitless because the concentration values we use in the calculations are all relative to the standard concentration. That is relative to 1 mole per liter. But what is the equilibrium constant even mean? A large equilibrium constant, that is if K is greater than 1. Means that the reaction is product favored. It will tend to make more product that reactants. A small equilibrium constant, that is if K is less than 1, means that the reaction is reactant favored, and it will tend to make less products than reactants. So let's consider another reaction. Carbon tetrachloride decomposes at 700 Kelvin to make elemental carbon and chlorine gas. The concentration equilibrium constant of that reaction should be equal to the molarity of the products raised to the power of their coefficients divided by the molarity of the reactant raised to the power of its coefficient. However, carbon is a solid, so what is its molarity? The molarity, or more correctly activity, of any solid or non-homogeneous reactant of product has a value of 1. That means that we can exclude all solids or non-homogeneous chemicals from the equilibrium expression. So the molarity of carbon should be erased. In addition, solvents typically have an activity of 1 and are not written in the equilibrium expression. So let's try another problem. Suppose that 1 mole of carbon tetrachloride is added to a 5-liter flask and heated to 700 Kelvin after the reaction reaches equilibrium. So there are 0.88 moles of carbon tetrachloride remaining. Calculate the equilibrium constant of the reaction when faced with a problem like this. The best way to solve it is to set up a rice chart. That's right. So rice, whenever you solve an equilibrium problem, just picture a big bowl of rice. The R stands for reaction, and we already have our balanced reaction written. So the I stands for initial molarity, the C stands for change in molarity, and the E stands for equilibrium molarity. So be sure to actually write out our IC so that you don't skip anything or make a mistake. So the question tells us that we are starting out with an initial amount of 1 mole of carbon tetrachloride in a 5-liter flask. So we can calculate its initial molarity using equation M equals N over V, which is 1 mole divided by 5 liters, or 0.2 molar. So we put the 0.2 directly under the CCl4. So we can ignore carbon because it is a solid and there is initially no chlorine gas, so we put a 0 underneath Cl2. So as for the change in molarity, we know that the reactants are decreasing by a certain amount, so we put minus X for CCl4, and the coefficient tells us that the Cl2 are made for every 1 CCl4 that is lost. So we put plus 2x for Cl to equilibrium molarity, simply the initial molarity plus the change molarity, so that is 0.2 minus x for carbon tetrachloride and 2x for chlorine. Now, how do we figure out x looking back at the problem? It says that there are 0.88 moles of CCl4 at equilibrium, so we can calculate the equilibrium concentration of carbon tetrachloride, which is a 0.88 moles divided by 5 liters, or 0.176 molar. The equilibrium molarity of CCl4 is also equal to 0.2 minus x. If we add x to both sides and subtract 0.176 from both sides, we can calculate x to be 0.2 minus 0.176, which equals 0.024 now. Now the only thing left to plug in the numbers and calculate the equilibrium constant. Kc equals the equilibrium molarity of chlorine squared divided by the equilibrium molarity of carbon tetrachloride. So the equilibrium molarity of chlorine is 2x, and we can substitute 0.024 in 4x. So we already calculate the equilibrium molarity of CCl4 to be 0.176. Plugging this into our calculator gives us an equilibrium constant of 0.013. Does this number make sense? So does this number make sense? Yes. The concentration of reaction is larger and the concentration of product at equilibrium, so an equilibrium constant less than 1 makes sense. So here's the steps. So for solving involving several equilibria. So first, we have to write the balanced chemical equations. We have done that, just like what I have said earlier. And set up equation for a known quantity, write equilibrium constant expressions, write mass balance expressions, write charge balance expressions, count the number of equations and the number of unknowns. Now, if yes is no equation, no unknown, so make suitable approximation, solve equations for unknown where approximates valid. So the problem solved. If no, so stop problem unsolvable. So approximations can be made only in charge balance and mass balance equations. So never in equilibrium constant expressions. So for problem 1, so I've prepared here 5 problems. So here's problem number 1. So the reaction between gaseous sulfur dioxide and oxygen is a key step in the industrial synthesis of sulfuric acid. So a mixture of SO2 and O2, or sulfur oxide and oxygen, was maintained at 800 Kelvin until the system reached equilibrium. So the equilibrium mixture contained 5.0 times 10 raised to the power of negative 2 moles SO3, 3.5 times 10 raised to the power of negative 3 m molar O2, and 3.0 times 10 raised to the power of negative 3 m SO2. So the question is, calculate K and Kp at this temperature. So the given, the balance equilibrium equation and composition of equilibrium mixture. So what is asked? So equilibrium constant. So the strategy, write the equilibrium constant expression for the reaction, then substitute the appropriate equilibrium concentrations into this equation to obtain K. So here's the solution. So after we balance, so we substitute the appropriate equilibrium constant into the equilibrium constant expression. And then we solve for Kp. So we use the relationship derived previously. So then we plug in and then calculate. So the result is 1.2 times 10 raised to the power of 3. So for problem number 2, so here's the problem number 2. So a 1.00 mole sample of nitrogen NOCl was placed in 2-liter reactor and heated to 227 degrees Celsius until the system reached equilibrium. So the contents of the reactor were then analyzed and found to contain 0.056 mole of CO2. So calculate K at this temperature. The equation for the decomposition of NCl to NO and Cl2 is as follows. So the given is balance equilibrium equation, amount of reactant, the volume, and amount of one product at equilibrium. So what is asked is only the K, which is to calculate. So here's the strategy. Then the solution. Just follow the strategy, and then you will get the solution for this. And then we get this answer, which is 4.5 times 10 raised to the power of negative 4. So here's problem number 3. So in this problem, the given is balance. We have balance equilibrium equation, the K, and initial concentration. So we already have the initial, so we get to know its final concentrations. So use this strategy. So the solution is here. So you can check your work by inserting the calculated values back into the equilibrium constant expression. So the two significant figures, this K is the same as the value given in the problem. So our answer is confirmed. Here down to problem number 4. So in here, this problem, the given is balance equilibrium equation, concentrations of reactants, and K. So what is asked? The composition of reaction mixture at equilibrium. So here's the strategy. And then the solution. Just plug in. So first, don't forget to first is balance, and then use the appropriate equilibrium equation, and then answer what is asked, and then plug in the numbers, and then calculate, and after that you will get your answer. So last is problem number 5. So in here, so the given is balance, equilibrium equation, and values of K, P, PO2, and PN2. So in here, the equation is already balanced. So what is asked is the partial pressure of nitric oxide. So here is the strategy. And then the solution. And in here, we plug in the numbers, and then we get the answer, which is 2.0 times 10 raised to the power of negative 31. So that's it for today. I hope you learned something.